Hello, let's look at section 4.5 today, the day 3 one. We've been working on U substitution. And today I want to just go through some more of the difficult problems. So we're going to look at kind of a change of variable method. What does that mean, huh? So we're going to look at that. The other thing we're going to do is substitute using definite integration. So like where I have definite bounds, a definite integral. How do I handle that in the U substitution method? Your homework will be this day 3 worksheet that should be in your note packet. Okay, so let's just give this a whirl. The change of variable method, I like to refer to it as a double substitution method, and you'll hear me call it a double sub just because we will end up substituting twice. So I bet you can see we're going to start out with what we typically do, and that is a U substitution. So let's let U equal 2x minus 1. Du then will equal 2 dx. But I'm noticing I have an x dx. Well, I'm not going to be able to take care of the x, am I? I'm going to be able to take care of the dx. So 1/2 du is equal to a dx. And that's what's different about this one. You might think, oh, I can't use U substitution because what do I do with this x that's kind of hanging out there? Well, that's what this is all about today. So we'll just kind of proceed through. All right, so we've got some things we can sub for. The x is a problem, so I'm just going to keep that in red for right now because I haven't subbed it out. This is u, 2x minus 1, so I'm going to have a u to the 1/2. And dx is a 1/2 du. And then I've got that glaring x hanging around, don't I? I need to get everything into u's. So here's the little trick we're going to do. We're going to take our u statement and solve it for x. And we'll figure out what x is in terms of u. All right, so that should be fairly easy to solve, shouldn't it? How do you erase that? There we go. All righty, so let's solve for x. That means I'd have u plus 1 equals 2x, or 1/2 u plus 1 equals our x. Now I have a value that I can put in place of x, and that's what we're going to do. So instead of x, I'm going to put in 1/2 u plus 1, and then I'd have my old u to the 1/2 du. So just doing some math here, let's just keep simplifying. This 1/2 and this 1/2 can make 1/4. I'm going to have u plus 1, I'm going to make a separate line just so it's more obvious, times u to the 1/2 du. That looks like we should distribute, doesn't it? Let's make this into a polynomial because, you know, integrating a polynomial is very easy. Oops, don't integrate yet, Cindy. I guess I'm not. U to the first, u to the 3/2 makes, or 1/2 makes 3/2. Add those exponents. Plus a u to the 1/2. And then it gets multiplied by du. Now I'm ready to integrate, so I get 1/4. U to the 3/2, that's going to be a u to the 5/2, so multiply by 2/5, plus u to the 1/2 plus 1 gives us 3/2, so multiply by 2/3. Add a c, since we have an indefinite integral. And then it's going to be distribute, isn't it? 2/20 is the same thing as 1/10. Something to the 5/2. I got to stretch back up and look what was u equal to 2x minus 1. So 2x minus 1 replaces our u, doesn't it? plus 2/3, replace u with 2x minus 1 to the 3/2. Got to close that parenthesis, plus c, because I have, you know what? I got to back up, you guys. I just was looking at this. I don't need a parenthesis here. I was thinking the 1/10, but then when I look back, it's 1/4 times this. So 2/3 times 1/4 would be 2/12. How about 1/6 on that? Just to double check. Always a good idea to look back over your work, and something wasn't quite feeling right on that. Perfect. Take a moment, pause if you need to, and walk through those steps again. I'm ready to move on to problem B. Okay, problem B. Here we go with problem B. Let me shove that one out of the way. Problem B. What do you think you should choose for your U? I think I should choose the bottom. It looks more complicated, doesn't it? Oh, it's not letting me write. It looks more complicated. It's got the square root. And so I'm going to go with just the x plus 4 portion, x plus 4. Because the derivative of that would be dx. All right, so we can see there's going to be some stuff unused or unable to sub for yet, but don't worry, we've got some tricks up our sleeves for that, don't we? So let's rewrite this integral now in terms of u, at least the u portion that we know. We got u to the 1/2 on the bottom. Dx and du are equivalent in this case. And I'm sitting with the problem of 2x plus 1. So I need to solve this for x, which would look like u minus 4, wouldn't it, equals x. So now I can take u minus 4 and put it in for x. So this will create an integral of 2. What are we putting in for our x? Oh, that's right, u minus 4, and then plus the 1, all divided by u to the 1/2. And you're probably thinking this is a total mess, and you're right. But good thing we've got some great algebra skills, because we're going to use those. We're going to try and simplify as much as possible. So I'm just distributing. I distribute it along the top, right? 2 times u, 2 times -4 gives us 2u minus 8, plus the 1. Keep simplifying. So I get the integral of 2u minus 7 over u to the 1/2 du. Now, you know all about these type of fractions. They're the ones I love. And let's simplify this. So where is that taking me? Well, it's going to give me an integral of 2u over u to the 1/2 minus 7, I'm going to call it u to the negative 1/2 du. Am I ready to integrate? Not quite. I'm going to get this first thing simplified down. That'd be a u to the 1/2 minus 7u to the negative 1/2 du. Okay. I think it's time to find the antiderivative. So we are actually going to integrate at this point. That will be a 2 u to the 3/2 multiplied by 2/3. Subtract the 7, u to a positive 1/2. Divide by half is like multiplying by 2 over 1. And then we've got our plus c. Simplify again, 4/3. Might as well replace the u at this point. That u was x plus 4. Gets raised to the 3/2 power. Minus 14. Replace the u with x plus 4. Raise it to the 1/2 power plus c. And abracadabra, we got the answer. Good enough. That's pretty complicated, isn't it? That's a pretty complicated antiderivative to our integral. And this U substitution is just an awesome technique to really help keep us organized and proceeding through in a manner that we can actually find answers. So that's what I refer to as a double sub. You're going to find that not everything completely subs out from our simple U sub, but there are ways to help ourselves out if we can solve for x and rewrite x2. All right, on to a definite integral. When we integrate over an interval of a to b, those a and b values are really truly x values because this entire integral is in terms of x's. So it would make sense then that our bounds are as well, right? We've seen them graphed out. We know what, graph it out. We're going from 0 over to 1 in this case, let's say. Not the picture that we're after, but you get the idea of what those bounds mean. If I switch to U substitution, I could update my bounds to be in terms of U. Or I could switch back to x's like we have been doing and use x values. So I think this first one, I will show you both techniques so you can do a comparison on it, and we'll go from there. So the first technique, I'm going to do our typical U substitution, switch back to x's that we're quite familiar with. So I think you probably all can see that we should let U equal x squared plus 1. Then du is 2x dx, but we just need x dx, don't we? So we need 1/2 du to be equivalent with x dx. And that should set us up in our U substitution process. All right, so I'm going to come over here. I'm going to leave my bounds off on purpose. X dx was a 1/2 du. And then I have u to the third. The reason I'm leaving my bounds off is because it would be inaccurate, well, it'd be just plain wrong, if I put 0 to 1 on, because these are x values. My whole integral is in terms of u. Now, if you did it on the AP test and you wrote that those were x values, they will go along with you then. They realize that you understand that you have a mismatch of variables going on, and you're kind of in an intermediate stage of working through the problem, and they will allow that then. All right, so I'm going to have, let's actually integrate this. U to the fourth divided by 4 or multiplied by 1/4. I don't need a c value, do I? We know that this would be at x equals 0 to x equals 1, but I can't really make use of those because I'm sitting in terms of u. So this would be a 1/8 u to the fourth. Let's replace u with x squared plus 1 raised to the fourth. Now it's appropriate that we can actually integrate because everything's in terms of x's. It's kind of like the world is balanced again. All right, so we have 1/8. Plugging in 1 first, I would have, let's see, 1. We'd have 1 squared plus 1. That would be 2 to the fourth minus put in 0. And I'd have 0 plus 1, 1 to the fourth. Take away, oh, hold it. What did I do there, guys? No, that's right. Okay, hang on a minute here. When I put in 1, I had 1 plus 1 is 2 to the fourth. There's my f of b. And then plugging in 0. So this was f of 1, wasn't it? Minus f of 0. I kind of lost track there. Put in 0, and I'll have 1 to the fourth. All right. That gives me 1/8 of 16 minus 1. Final answer will be 15/8. If you want to check it, you could certainly put this in your calculator and come up with the answer, right? Because our calculators can do the numeric integration. So 15/8, remember that number. Actually, I think what I'm going to do is kind of tie this stuff together. I want to shrink it down a bit. right, let's see if we can shrink that down. And we'll just kind of keep track of it over here. Where's the answer? There's the answer. We'll swing that over there with it. Because I want to do a comparison on that method versus this next method. Okay, come back here, eh? Let's do it using U substitution where I update my bounds. I'm going to change the bounds so that they are in terms of U as well. So if you need another sheet of paper, please grab it. So U, same thing. U equals x squared plus 1, no difference there. du equals 2x dx. Then we had to go 1/2 du equals x dx. Okay, so our U sub box looks identical to last time, shouldn't it? And this portion where we integrated will look the same as well. X dx is a 1/2 du. X squared plus 1 is the U, so u to the third. Now, here's the part that changes. It calls for a new color, doesn't it? I want to change the bounds. Write this down. When x is 0, I'm going to start with my lower bound. What would u be? Good question. But if I look back up to my sub box, it tells me what u is. U is 0 squared plus 1 then in terms of x, isn't it? U turns out to be 1. Okay, so it's on the bottom, it stays on the bottom. I replace 0 with 1. When x, choose a different color. When x is the upper value of 1, u becomes 1 squared plus 1, or 2. So I replace the upper bound now with 2. These are now sitting in u values, which is perfect. This entire integral is just fine. It's all in terms of u. And I am not going back to x's now. So let's keep integrating. Well, we know the story. It's 1/4 u to the 4th. And my bounds are going to be from 1 to 2. Remember last time, our bounds, we came back, or we said they were in terms of x's. They were x equals 0 and x equal 1. Well, these bounds are in terms of u. So now I have 1/8 u to the 4th evaluated from 1 to 2. So that's going to be an f of 2, 2 going in, 2 to the 4th, minus 1 to the 4th. Oh my gosh, these turned out to be identical values, didn't they? You'll notice I did not switch out of u, so it saves a step. I like it. The AP also loves it because they give you multiple choice questions that you have to use U substitution throughout the entire problem. So 15/8, winner, winner, chicken dinner, answer's the same. So there are two different methods. If you really have an affinity to coming back to x's, I guess you can. If you want to take the easy way, then just proceed using u's. But you got to remember to change to u's on your bounds. All right. I think, you guys, I'm going to go ahead and pass on B because I don't want to get this video so long that you can't, or that you get sick of me, which you probably already are. All right. This next one. Once again, you can choose to either back sub your expression in terms of x or keep the original boundaries in terms of x. Or you can change everything to u's. The choice is up to you. But on the AP exam, most of the time, you guys, they're going to set up a problem where they ask you to use U substitution. Matter of fact, they even give you the value of U. So you've got to follow their lead and see if you can make sense of this. So let's try it. They suggest that U is equal to x over 2. So we'll play with that. That means du is equivalent to a 1/2 dx, right? Because this is really 1/2 x, and if I take the derivative of that, it'll become 1/2 dx. Oh, yikes. I got the dx. So I'm just going to be very deliberate in my substitution. So things that I know I can change. I can change x over 2 to u. I can change dx to 2 du. I haven't accounted for this x yet, but we know how that's done. That is that extra substitution technique. So I'm going to take my original u substitution and solve for x. So x is equal to double both sides and we get 2u. Now I've got this figured out. The last thing I need to do, remember these are x values, x equals 2, x equals 4, is I need to update my bounds. So I'm going to sort of get this started so far. I have 1 minus u squared. Dx is 2 du. Okay, we got that. It's over an x, but that x is equivalent to 2 u's. Ooh, I bet you see that's 2. Let's cancel those 2's. So now I'm sitting with an integral of 1 minus u squared over u du. The only thing that I'm missing are my bounds. And these bounds that they're showing are all in terms of u. So now we have to change our bounds into u as well. So if you don't mind, I'm going to erase right here. I'm just going to erase all this. Give me a little workroom off to the side here. We had u, as suggested by them, as 1/2 x. So when x is 2, right there, what would u be? U would be 1/2 times 2, or 1. 1's going in my bottom. When x is 4, then u is equal to 1/2 of 4, so u turns out to be 2. All right, now, is there an answer selection that matches mine? I'm liking D. So that's kind of what the AP plays with you. They will force you to change these bounds. And so it's just a good technique. It really is, I think, faster, easier, all of that, to just stay and use on a definite integral. There's another one. I think we'll do that one in class tomorrow. And then let's save this for tomorrow, too. We can talk about, well, no, let's talk about this now, because that'll help you on your worksheet. So it says integration of odd and even functions. We know some things about odd and even functions. And sometimes they can be a real advantage to understanding if it's odd or even. So if f is even, let's draw ourselves an even function. I'm thinking a nice quadratic. Quadratic's an even function. What makes it even? Well, the fact that it is symmetric over the y-axis, right? So if I'm looking for area underneath the curve, let's use a highlighter. That would be this region here. I'm going to call that out to A. And then I'd have equal area on the opposite side, right? So let's put in where we are establishing our bounds. Let's call this negative A and this one positive A, equal distance from the y-axis. So we got x and y going on as well. And what do you notice about the area from negative A to positive A? Well, I get repeats in each of those regions, right? So I can say that that entire region is equal to twice the value from 0 to A of f of x dx. I can use the idea of symmetry and make an easier integral 0 to A out of it. So I'm just looking at, okay, here's this half. If I double this side, I will pick up that area, okay? Odd functions, let's talk odd functions before we move on. So an odd function, let's think about like a cubic, right? That's kind of an easy one to talk about. Let's put an A and a negative A, equal distance from our y-axis and our x-axis, highlighting the region between the x-axis and our curve, would be right in there. X-axis and our curve. And what do you notice this time? First thing I noticed, I got positive on one region and negative area on the other region. Are those regions equivalent? Yes, they are. So this actually turns out to be a value of 0 for an integral that is an odd function balanced over the y-axis from negative a to positive a. So know those properties about odd and even, because sometimes they can really help you. So we are given a starter. They tell us that, okay, f is even and it's equal to 3 from 0 to 5. So negative 5 to 5 of an even function would tell me, okay, I can just double the sides and integrate from 0 to 5. Integrate half of the region and double the area, and I should have the equivalence of negative 5 to 5. So it looks like this would have a 6 to it, doesn't it? If I know 0 to 5 is 3, then I also know that negative 5 to 3, this other portion, the other side, would be 3. And we know this property of a scalar, we can bring it out front. So 4 times negative 5 to 5 of f of x dx can be thought of as 4 times, since it's an even function, 2 from 0 to 5 f of x dx. Cutting that boundary in half gives me 8 times a value of 3, so I would come in with 24 units. Use your picture or draw a picture, sometimes that might help. All right, we are given that we have a value of 3, so if I even just wanted to, I could say, you know what, the area underneath this curve is 3. What would that force this side to be? Negative 3. So if I go from negative 5 to positive 5, I could even draw it here if it would help so that you have a picture going, guys. I'll get a cubic in here and maybe shade a little, huh? Here's that region. Let's shade the other region green, maybe. There's equivalent region green. I know I've got some positive, some negative. Now, negative 5 to 5, this would be a negative 3. This would be a positive 3. I'm picking up from there. This would be then negative 3 plus positive 3 gives us 0. And finally, last one, negative 5 to 0 is going to be the opposite area that this one had, so I know that answer is negative 3. And the last one, well, this would say 4 from negative 5 to 5, f of x dx. Well, 4 times 0 still is Zippo. Okay, so kind of a long video. I hope you take some pauses as you go through. This is the homework. I think you'll be able to do it. Some of them you can see are out of our textbooks, so you could look at solutions online if you had to. This is like an AP one, multiple choice, and there's my answer key. I think the answer key is on Schoology, so if you want to use that, you certainly can. All right, and then, oh, good, your favorite, some left Riemann sum, right Riemann sum. Ooh, average value. Remember average value, 1 over b minus a, the integral from a to b. And we're going to integrate this or estimate it using a Riemann sum. And the last one. All righty. Have a good day, you guys. Bye-bye.